In this video, I want to do a Fourier series example. So let's find the Fourier series for f of x equals the absolute value of x on the interval from -1 to 1. So seeing this interval, I know that my value of L here is 1. So L equals 1. So let's talk about how we solve this. We need to figure out what the coefficients are. So remember, we're trying to write f of x, we're trying to approximate it in the form a0 over 2 plus the sum from n equals 1 to infinity of a sub n times cosine of, in this case it would be n pi x over, our value of L is 1, so that's our denominator, plus bn times sine of n pi x over L is 1. Okay, so we are trying to find what the coefficients are. All right, so let's begin with the a0 over 2, with this constant term. So a0 over 2, remember in the previous video we talked about a formula for this. It's going to be the inner product of f of x with the constant function, and then divided by the constant function 1 with itself. That was the formula that we saw in the last section. So each of these is an integral. So the top is the integral from, in this case, L is 1, so -1 to +1 of f of x times 1. And then the denominator is the integral from -1 to +1 of 1 times 1. Sorry, and both of these need a dx. So dx and a dx. All right, so f of x, our function, let's go ahead and actually write down what that is. F of x, our function, is the absolute value of x. Okay, so the absolute value of x times 1 is the absolute value of x. And that is an even function. So seeing that it's an even function, we can rewrite the numerator as 2 times the integral from 0 to 1. And what is the absolute value of x equal on this non-negative interval? So the absolute value of x just equals x if x is greater than or equal to 0. So because my interval is from 0 to 1, the absolute value of x is just going to simplify to x. And that'll make it easier to integrate. All right, and the denominator, well, what's the antiderivative of 1? That's x. And we got to evaluate that at -1 and +1. So x evaluated at -1 and +1. All right, so now let's go ahead and do the antiderivative on the numerator. So we need to take the antiderivative of 2x, which would be x squared, evaluated at 1 and 0. And the denominator, we plug in 1, and then minus, plugging in -1, so minus -1. So in the numerator, we end up with 1 minus 0. The denominator is 2, so overall we get 1/2. All right, so we know what a0 over 2 is. We know what our first sort of coefficient should be. Let's move on to what a sub n should be. So we got this a0 over 2. Let's figure out what a sub n is going to be now. So what will a sub n be? All right, so for a sub n, we have a formula for that as well. Our formula for that was, for that one, you take the inner product of f of x with cosine, with a cosine term, cosine of n pi x, technically over L, but L is 1, so we could just write this. So technically the denominator of this would be L, but in our problem, L is 1. So we get this, and then you divide this by the inner product of the cosine term, cosine of n pi x, with cosine of n pi x. So in other words, this coefficient represents what the coefficient is when we project our function f of x onto this cosine function. All right, so both of these are going to be integrals. So the top is an integral from -L, which in this case is -1, to +1 of f of x, and f of x is absolute value of x. Let's go ahead and write that in. Absolute value of x times cosine of n pi x dx. The denominator is the integral from -1 to +1 of the cosines multiplied. So that's cosine squared of n pi x dx. Okay, so there are a couple of computational tools that are useful for evaluating these Fourier coefficients that will show up again and again, especially in the denominator. So here are the computational tools, beyond just using even and odd stuff. So when you have an integral from negative L to L of either the sine squared term or of the cosine squared term, both of those are going to be equal to L. Okay, one of the ways you can show why is to use trig identities. So I won't go through the whole derivation. I'll just mention trig identities. Briefly, what trig identity we could use for this sine squared term, for example. So for the sine squared, notice that sine squared of theta equals, what does it equal? It equals 1 minus cosine of 2 theta over 2. So we could use that, for example, to evaluate this sine squared integral. All right, so for our problem, that's useful because this denominator, this integral from -1 to +1 of cosine squared, that should be equal to L, but in our problem, L is 1. All right, so now let's continue our computation. So we got up to here. So the next thing that I want to notice is, with this integral on the numerator, what we have, thinking about even and odd functions, the absolute value of x is an even function. Cosine is also an even function. These are both even functions, And an even function times an even function is an even function. But you should check this. Remember, even and odd functions don't work like even and odd integers. Okay, so this ends up being an even function. So the numerator we could write as being 2 times the integral from 0 to 1. And on the interval from 0 to 1, absolute value of x becomes just x, like we saw before. And the cosine stays how it is, cosine of n pi x. And the denominator we now know is 1, and that's why I don't need to write that. So now we have to take the antiderivative of x times cosine of n pi x. At this point, I'd encourage you to pause the video for about 1 minute and see if you can remember how to integrate something like this. 4, 3, 2, 1, pause the video. Pause the video and see if you can remember how do we take the antiderivative of something like this. So this is kind of reviewing some calculus now. So hopefully you did that. Hopefully you've paused the video for a minute, just a minute, to try this. If not, go ahead and do so now. So it turns out the technique that we need to use is integration by parts. We got to integrate this thing by parts. Or sometimes I'll refer to integration by parts as IBP. Okay, so for integration by parts, I need to write down what u is, what du is, what dv is, and what v is. Okay, so I begin by writing down what u and dv are. So u, I'll let it be x. dv, I'll let it be the other stuff. Oh, and actually I forgot to write the dx here. All right, so dv is going to be the other stuff. It'll be the x. Sorry, no, I got the x already. It'll be the cosine of n pi x dx. So now let's write down the remaining stuff. Du, the derivative of x, is 1 technically, but I write, technically it's 1 dx. Okay, and then the antiderivative of cosine of n pi x would be, it would be sine of n pi x, but divided by the constant here, the n pi. All right, so we got the setup for integration by parts. Now let's go ahead and plug those things in. So what we have is we have 2 times, we'll get uv, which is x times sine of n pi x over n pi, evaluated at 0 and 1, minus the integral from 0 to 1 of v du. So v will be, I'll get a sine of n pi x over n pi, and that's multiplying the 1 technically that's in du, and then we also write the dx that's in du. Okay, close that bracket. All right, so what we have here is we have 2. So now if we plug 1 in for the x, what we end up with is we end up with sine of n pi over n pi. If you plug in 0, you'll get 0 times something, which is 0. So minus 0. Okay, and then if you take the antiderivative of sine, it's negative cosine. But the negative will cancel with this negative to make it positive. So we'll get cosine of n pi x. But an n pi will sort of pop out and go to the denominator. So the denominator will be n pi squared. If you don't see how I got that, do a u substitution on this. All right, so we evaluate this at 0 and 1. All right, so let's continue to simplify this. All right, so the first thing that I want to notice is if you take sine of an integer times pi, like sine of 1 pi, or sine of 2 pi, or sine of negative 5 pi, or negative 7 pi, that is always going to be 0. Okay, so now what we have is we have 2, oh, whoops, let's write this in black. We have 2 times, and if you plug in the 1 into the cosine term, we get cosine of n pi over n pi squared. And if you plug 0 into that term, what you would get is you would get minus cosine of 0 on the top, which is 1, and then over n pi squared. Okay, but cosine of n pi is equal to negative 1 to the n. So what this whole thing becomes is we have 2 times negative 1 to the n. So times negative 1 to the n minus 1 on the numerator, and then n pi squared on the denominator. All right. So this whole thing, this is a sub n. This is a sub n when n is not 0. These are going to be the coefficients of the cosine terms. So let's highlight this. I'm sorry about that. I kind of shifted out of place there. Okay, so that's a sub n. So finally, we need to get what b sub n is. So the coefficients of the sine terms. All right, so the coefficients of the sine terms. So this time we're projecting onto the sine terms. So we'd get f of x inner product with the sine term, sine of n pi x. And then L is 1 technically, so I don't need to write a denominator. All right, so L here is 1. That's why I'm not writing the denominator. And then divided by the inner product of sine of n pi x with itself, sine of n pi x. So if we write down the integrals for each of these, the top is negative 1, sorry, it's a positive 1. My function was the absolute value of x, and then multiplied by sine of n pi x dx. And the denominator is the integral from negative 1 to positive 1 of sine times sine, which is sine squared of n pi x dx. All right, so we need to simplify this now. So notice that in the numerator here, absolute value of x, that is an even function. Sine x, that is an odd function. And an even function times an odd function, we've seen what this is before in the videos from this lecture. This is an odd function. All right, so the numerator is an odd function. The denominator, remember, we said what the integral from negative L to positive L of the sine squared term is in our computational tools that I talked about earlier in the video. So where was that? Let me just scroll to it. A little bit more down. Yeah, the integral from negative L to positive L of sine squared, the sine squared terms that show up in my Fourier series, those are going to be L. So let's use that. So this integral is going to be L, but in our problem, L is 1. So that whole denominator is 1, so that's nice. All right, so what we end up with now is we have an integral from negative 1 to positive 1 of an odd function on top. An odd function dx. And the denominator is 1, so I don't really need to write that, but I could put it just over 1. But the integral from negative L to positive L of an odd function is 0. So the top is 0, the bottom is 1, so that becomes 0. So that's nice. Using even and odd functions let me drastically simplify this computation here. All right, so this is Bn. This is going to be the coefficient of our sine terms. All right, so we've figured out all the coefficients. What's left to do now is just write down our Fourier series for our function. So thus, for our function, which is absolute value of x, it's going to be approximately equal to, so a naught over 2, remember, was 1/2. That was our constant term. And then we're going to get plus the series from n equals 1 to infinity. And then I write a sub n first, the coefficients of those cosine terms. So that was 2 and then times -1 to the n minus 1 over, and it was n pi squared on the denominator. That times the cosine terms, cosine of n pi x. Okay, so these were the coefficients of the cosine terms. And the coefficients of the sine terms were 0. So technically it would be plus 0 times all the sine terms. So we don't need to write those. So that is the Fourier series for our function, for the absolute value of x. So one thing that you might notice about this is there were no sine terms here. There were just cosine terms. It turns out that when our function that we're trying to write the Fourier series of is an even function, like the absolute value of x, we can express it purely in terms of cosines. When it's an odd function, we'll be able to express it purely in terms of sines. And that makes sense, I think, intuitively, because cosines are a bunch of even functions. Sines are a bunch of odd functions. And then it'll also turn out that when our function f of x is not even and it's not odd, when it's neither, then the Fourier series will involve both cosines and sines.